Alright, so our lesson for 5.6 in our Pearson textbook is a very brief intro into the fundamental theorem of algebra. So it sounds really scary, right? It's a fundamental theorem and all. And it does have a really large base component of algebra. There's a lot of things that go into the fundamental theorem. We're going to talk about a few. We're going to keep it real basic. And we're going to have to use our skill of synthetic division coming up in this lesson. So if you don't know what it means to synthetically divide polynomials, you're going to have to go back and watch that lesson. So we're going to be doing kind of halfway fundamental theorem. There's a whole other component to it that we're not going to talk about. It's how we had to do these problems back in the day before graphing calculators, and they weren't a lot of fun. You had to make some guesses, some educated guesses, and then kind of do a lot of work to figure out what the x-intercepts were going to be. We're going to cheat a little bit. So here's a note at the bottom of the screen. It says, note, you will find the same number of solutions as the degree. So if you have a quadratic, you're going to find 2 solutions. They might not be unique, but you will find 2. If you have a cubic, you'll find 3. If you have a quartic, you'll find 4. And then there's another note here about a vocabulary term called multiplicity. This is a new one for us today. And if you notice that the graph, when you look at the graph, it does something like this, where it seems to bounce off the x-axis right here. So that's what I refer to as a bounce. That means that we have what's called even multiplicity, meaning the root shows up 2 times or sometimes 4 times. So for our class, as an introduction to this topic in Algebra 2, we're going to keep it real basic, and typically when we see multiplicity, we're going to see multiplicity of 2. Next year in pre-calc and college algebra, you will talk more about different types of multiplicity and what that means and what it looks like. So for here, just a very basic intro. So we need to find all the zeros of the polynomial function. So right now I have a cubic, and I can use algebra techniques on this particular one because it does factor nicely. But I'm going to show you another technique, and then we'll come back and I'll show you what the factoring looks like, because you can have 2 options, right? Not all of them are factorable, though, at least not easily. So what I want you to do is grab your graphing calculator and type x to the third minus 4x squared plus 3x into y equals. I'm going to pause the video and we'll come back. So go ahead and pause your video and get that typed in. So in my y equals menu, I have my function typed in. And I just want a standard viewing window. So zoom 6, and I see this polynomial. So what I need to identify is where this function crosses the x-axis. I'm feeling like this and this and this are the 3 x-intercepts. And if you're not sure, if you're thinking maybe your eyes are deceiving you, what you can do is you can hit trace, and you can type in your guesses. Now right away it pops up as 0, 0. So that tells me x equals 0 is one of the x-intercepts. So I'm going to jot that down. And what we're going to do next is we are going to use successive synthetic divisions, where the zeros that I found on my calculator are going to be the things that we divide by. So the 0, the root, the solution, goes in that little half box. And then we set up synthetic division. Remember, it has to go all the way down to the constant, and there's no constant here. So we're going to set up our coefficients as 1, -4, 3, and 0. So for synthetic division to work, we bring down our first lead coefficient, and then we start multiplying and adding. So 1 times 0 is 0. And then we add these up and get -4. And then -4 times 0 is 0. Where are we at? 3 plus 0 is 0. 3, excuse me, that would have been bad, huh? 3 times 0 is 0, 0 plus 0 is 0. So when you do synthetic division on something that you know is a factor or a root, this last number, the remainder, should always be 0. It should be nothing left over because it should divide it evenly. So what you have now is we took a cubic polynomial and we knocked it down to 1 level, so we knocked it down to a quadratic. We have 1x squared minus 4x plus 3. And if I'm supposed to find all the zeros, what I can do now is I can take this quadratic and find the solutions through one of my many algebraic methods. And for Algebra 2, primarily we're going to give you ones that factor. Now if you're not sure if it factors or you don't like factoring, you can use quadratic formula. But I'm thinking this one factors pretty nice. The x squareds would multiply from x and x, and then multiplies to -3, arches that up to -4. How about a -3 and a -1? So if I was to solve these two, I would get x equals 3 and x equals 1. Now if I go back to my graph, and this is where I lose some kids because they're like, hey, I already know that answer. I could tell from the graph that the solutions were 0, 1, and 3. But what we're trying to practice right now in this unit is, can you use the fundamental theorem of algebra that states You can successively divide your existing polynomial by roots and then end up with a smaller polynomial that you could solve through any method. So like what we are going to find out in the near future is that not every quadratic is pretty and factorable. In fact, some of them just aren't nice at all. And sometimes the solutions aren't nice. So we have to have another alternative method. So what we're going to be practicing is I need you to do synthetic division as many times as you need to get it down to a quadratic. Once it's to a quadratic, we're going to go and find the solutions through an algebraic method. All right. So this one, x to the third power minus x squared plus 49x minus 49. I'm going to pause my video. You pause your video. You need to get it typed into y equals. So I have my function typed into y equals. And when I hit graph, standard viewing window is probably fine. I don't see much. So this is a good example. I do definitely see what I think is an x-intercept at 1. So to make sure that's what's happening, I'm going to hit trace, bring up the cursor, and then type x equals 1, and then hit enter. And if it comes out to y equals 0, then I guessed right. That is a x-intercept at 1. So on my calculator, or on my paper, I found from my calculator that 1 is one of the factors, or is one of the solutions. So I'm going to use synthetic division to knock this down. So using standard form coefficients, 1, negative 1, 49, and negative 49. Alright, remember we bring down that lead term's coefficient, and then we start multiplying and adding. 1 times 1 is 1, negative 1 plus 1 is 0. 0 times 1 is 0, that's 49. 49 times 1 is 49. And then like we said before, this remainder has to come out to nothing. If it comes out to a remainder other than nothing, that means you either messed up in your synthetic division. It's also possible that you thought the x-intercept was at one place, but it really wasn't. Alright, so what we had was a cubic, and then we knocked it down one level to a quadratic. So you have 1x squared plus no x is plus 49. And if I'm trying to find the solutions to this quadratic, it technically does factor if you know how to factor the sum of squares using i's. Otherwise, the rest of us would just solve this through square rooting, because there's just one x term in the problem. So if I subtracted 49 from both sides, we get x squared equals negative 49, and this is where we have to think back to last semester. When you square root negative 49, it's a 7i, remember, because it's like 49 times negative 1. But it's still an algebraic equation, so it's actually plus and minus 7i. So all my solutions are x equals 1, x equals 7i, and x equals negative 7i. Notice, and I didn't mention this on the last question, I found 1, 2, 3 solutions, and this was a cubic. I was supposed to find 3 solutions. So, excellent. That was a good case of, couldn't see all the roots in the calculator because 2 of the roots were imaginary. Uh-oh, quartic, which means we're going to have to do synthetic division twice to knock it down to a quadratic. So when I go to graph this, which I'm going to pause the video again, so are you, I'm going to be looking for 2 nice places where I think it crosses the x-axis, 2 x-intercepts. Alright, pausing. Alright, so we're back. I have my function typed into y equals, and remember I need to find 2 x-intercepts so I can knock the quartic down to at least a quadratic. I got plenty to choose from here, so I'm pretty sure this is x equals 1. And let's see, 1, 2, I'm pretty sure that guy's x equals negative 3. And I'm going to double check that by hitting trace. I'm going negative 3, that one I was a little leery of. Yep, that is a 0. And then how about a 1? Nailed it. Now, pretty sure I know these other 2, but what I'm trying to practice here is the successive synthetic divisions that knock it down to a quadratic. So it doesn't matter which one you start with. I'm going to go ahead and start with the negative 3. And lining up my coefficients in standard form order. 1, 5, 5, negative 5, and negative 6. Now remember, if we're doing this right, the remainder should be 0. So bringing down that 1 to start off the synthetic division. 1 times negative 3 is negative 3. Add them up, get 2. 2 times negative 3 is negative 6. Add them up, get negative 1. Negative 3 times negative 1 is positive 3. Add those up and get negative 2. And then that gives me a positive 6, which is 0. So we did well. Now remember, I'm still a cubic because it's too large for me to factor right now. So I'm going to do another layer of synthetic division on this blue and green part here with the other root that we found, which was at x equals 1. So same process. I'm going to start it off by bringing down the lead term, which is still a 1. And then we multiply. get 1. I almost said 2. Add this up and get a 3. Multiply, get a 3. Add that up and get a 2. Multiply, get a 2. And then awesome, no remainder. Must have done something right. So what we have left here is the polynomial knocked down to a quadratic. So far we found out that x was -3. We found out that x was 1. And now we're going to take this quadratic, which is 1x squared plus 3x plus 2. And we're going to find the next two solutions. So x plus 2 times x plus 1 is a good way to factor that quadratic, which gives me the solutions of x equals -2 and x equals -1, which is kind of what I thought was happening on the graph, but again, I have to practice this method. Now on your homework, there's going to be a part where it says write your polynomial in factored form. So what we're going to do is basically just kind of back up. If this is your solution, x equals -3, that means your factor was reverse it, x plus 3. And then this guy was x minus 1. And then if I just steal these factors back, I have x plus 2 and x plus 1. So these are the solutions, or the zeros, or the x-intercepts. And this is the polynomial in factored form. So I'm going to ask you for both things on your homework, so let's be prepared to give both. Uh-oh, another quartic. So same issue, I'm going to pause the video, you're going to pause the video, you're going to get your function typed into your calculator. Alright, we're back with the function typed into y equals. Again, I have a quartic. I need 2 x-intercepts to knock this down to a quadratic. So I'm going to make note of 2 obvious x-intercepts, which turns out I only see 2 right now, so that's good. I'm thinking this is x equals -1. And -1, -2, -5, which I'm going to confirm because I don't want to do all this work for no reason. So trace that -5 one. I'm a little worried I counted wrong. Nailed it. Alright, and then -1. Got it. Alright, so good news. We have to do successive synthetic divisions with those 2 x-intercepts. It's like a mouthful, isn't it? And then we're going to have a quadratic, which we're going to solve, and looks to me like our quadratic answers are going to be a little funky, so this is a good experience here. It doesn't really matter which one you do first. I'm going to go -5. And then coefficients, 1, 6, 14, 54, and 45. Alright, so bringing down that 1, and then multiply, and then add, multiply, add, multiply, add. Let's see, I always mess that up, 9. Multiply, and then again, our remainder should be 0. If it's not 0, we messed up. Now we're still at a cubic level, so I got to knock it down one more time. Let's go with our -1, the other guy that we saw on the calculator. Bringing down the 1. Alright, let's go all over again. Let's see, that's -1, add them up 0. This is a 0, add them up 9. It's a -9, and then again, I need a remainder of 0, which I have. So off to the side here, I found an x-intercept at -5, another one at -1, and then this quadratic is x squared plus 9. And I'm supposed to find the solutions. So this is another one where we're going to have to square root a negative, so we're going to have i's in our answers, which is fine because we know how to do that. If I square root a -9 in an equation, the answer is not just positive 3i, but also -3i. You can write them separately like this. That's the best way to write them, because you could say the 1, 2, 3, 4 solutions, because it's a quartic. For the factored form, this can get kind of crazy. Ready? You only want to write like normal-looking factors. So if I say x plus 5 times x plus 1, those are these two factors here. And then there's a couple different ways we can write these factors with the i's. I'm actually going to go back to this guy right here. Because that was an irreducible factor without using i's, I'm just going to leave it as x squared plus 9, but you might have an experience in the future where your teacher wants you to write x plus and minus 3i. So it depends. Whoops, x. Oh, for Pete's sake. Alright, let's try that again. So this term right here, your teacher might, not me, but in the future, x plus 3i and x minus 3i. They might want you to write them in that factored form. But for most pre-calc teachers, this is actually the version that they're looking for. So just keep that in mind for next year. I'm not going to ask you something so crazy on a test that looks like that. Alright, so here we're going to kind of go backwards. And I'm going to give you the zeros. So someone did all the work and found the zeros. Your job is to bring it back and write it. And the directions are going to say write it in like standard form. We're going to change this. I just want you to leave it in factored form. because otherwise that requires us to like distribute everything out and FOIL it out, and that's just a lot of work. I know you guys can distribute and FOIL, it's just not worth it. So let's name it p of x, because I feel like it. And if you have a 0 at 2, that means your factor is x minus 2. And then here you have 0 at 1, so your factor is x minus 1. Oops. And then a factor of a 0 at 4, so your factor is x minus 4. And it didn't say anything about what we call multiplicity, or we'll talk in a minute what that means, and also about I, so that is our answer. So here, very similarly, -2, -4, and -7. If I leave it in factored form, I get x plus 2 as the factor, x plus 4 as the factor, and x plus 7 as the factor. So it's just a concept of going backwards. Alright, now this one can get a little tricky. The 8 is not going to give you any issue. But when I say your polynomial has a solution of I, complex solutions come in complex conjugate pairs. So while I is one solution, his conjugate, which would be -I, is also going to be one of my solutions. So what we're going to set up is x minus 8 for a factor, and then x minus I is the factor they gave me, check, but his conjugate would be x plus I. Remember, conjugates are the good twin, evil twin pattern. So for us in Algebra 2, I would like you to leave your answer like this. When you move on in life to pre-calc, you'll see something a little more complicated. Alright, same thing here. The -5 is not going to give us any trouble. It's just x plus 5 for a factor. But when I tell you you have a solution of 2i, that means x minus 2i, I need the conjugate pair. So the conjugate to x minus 2i would be x plus 2i. So there's some hidden solutions and roots when they pull up conjugates that you have to be aware of. Alright, so there's one more concept that is not on our notes, but I still want to talk about it, and it's the concept of multiplicity. So let's say I end up with like a factored form of x minus 3 times x plus 4 to the second power. If I say list out all the zeros, this one has x equals 3, has a 0, and then this one would give you x equals -4. But do you see how there's a squared on it? That means that x plus 4 times x plus 4 shows up twice in factors. Whoops, 4, excuse me. So that means it shows up twice in your solution. So what we do to notate that is we say x equals -4 is a 0, but it has what we call multiplicity 2. And if I were to graph this function, 1, 2, 3, 4, 1, 2, 3. All right, we would see it cross through the x-axis at x equals 3, and then at x equals 4, it's going to bounce. So it's going to look something like this, and I don't, oh gosh. Okay, that was supposed to be curvy. It's going to look something like that when I graph it. We could go back and type this into y equals, and you'll see exactly what it looks like, but not like that. So that's the idea. When you see multiplicity of 2, that means the function is going to bounce off of where that x-intercept is supposed to be. Some books call that an x-intercept, and some books do not. I personally don't feel that this is an x-intercept. It is a 0, that's the right vocab, but an x-intercept means it crosses through the axis, so it depends on your teacher for that one. The other issue with the idea of multiplicity is if I tell you that you have zeros at x equals 5, -1, multiplicity 3. When you go to write your polynomial, you have to indicate the multiplicity with an exponent. So x equals 5 would be the factor x minus 5, but when your factor of x plus 1 has multiplicity 3, that means it shows up 3 times. So that's what your polynomial is going to look like for us when there's multiplicity of more than 1. Okay? So lots of practice coming your way on this. This is tough stuff. It's a really huge topic in algebra. We simplified it as much as we possibly can for Algebra 2. So there are ways to do it without a graphing calculator. It's just not a lot of fun. All right? Good luck.